Okay, recording. Yes, okay, welcome now to the computer vision study group. Yeah, once again, I don't know, it's the fourth or fifth session. I did one a while back. Now I'm doing one on the Swin Transformer um, with the subtitle Hierarchical Vision Transformer using shifted windows. It's quite an interesting paper that was released last year, middle of last year. And yeah, it was quite successful and became state of the art in different tasks. And we'll have a look at it today, a bit in detail, not all the details because there are a lot of details. And yeah, if you have questions anytime, just ask them right away, I would say. You don't have to wait until the end. Yeah, and I had much fun preparing the presentation. So, for example, this thing here, some animation. Wait, animation. Oh, there's animation. Because we're gonna do a bit of a Super Mario style, or maybe you saw my tweet. I called it Super Hagio style. And yeah, there's a little intro that I prepared. There's 3 slides. I spent 2 hours on them. And let's see. So, level 1, the CNN. Once upon a time, there was a Mario. His daily task was to look at images and tell his Yoshi what he sees on there. But one day, a convolutional neural network came along, and Mario got much better at his vision tasks. There comes the CNN. And Mario grows. Next level. Level 2, VIT, the Vision Transformer. There they are, Mario and Yoshi. Life was great, but after some time, Mario noticed that Yoshi looked different, so modern and fancy. Mario was getting jealous. Suddenly, a transformer came along, and Mario became all shiny and modern himself. Here comes the transformer. Oh, Mario is shiny and modern now. I hope Nintendo won't kill me for that, if that is on YouTube. And level 3 is Swin now. Let's see. Here's Mario in his fancy new environment. However, this new style was only a base for many more enhancements to come. For example, using shifted windows, Swin, for even better performance. And now, here comes Swin. And, it's a Mario Tanuki. So, in a way, that's not really related to our paper. But as I said, I had this idea and just had to do it. Yeah, that was the intro. Now let's do a little crossover with the Futurama. Need a vision transformer? Why not Zoidberg? Or why not VIT, right? So as VIT, or vanilla VIT as it is referred to, was the first really successful vision transformer, you can always ask, okay, why do we need anything else than VIT for our vision tasks? And there are multiple reasons, so just name a few here. So in the vision transformer in the vanilla VIT, we have a fixed size of image patches, right, that we use as tokens that we give into the transformer here. So they mostly are 16 by 16 pixels. That's what they use in their paper. And then they use these patches or tokens to compute global self-attentions on an image. And that can actually lead to quite high compute cost if you want to use a smaller patch size. So if, for example, use like 4x4 patches or something, right, to capture more details, you might want to turn it down a bit. But then you have a huge token length thing sequence. That's the word for it. And yeah, when you scale up the image, it will only get bigger and bigger. So it might in the end be quite a big computational cost that you just get there from trying to scale it up or trying to get more details. So that is not good. And that's what the authors of the Swin paper as well noticed. And then they thought about, okay, what can we do about it? And they came up with a Swin transformer, which is calculating self-attention not globally but in local windows, and applies patch merging between stages to get a more hierarchical structure, similar to convolutional neural networks. And through the self-attention in local windows mainly, you get this linear complexity opposed to a quadratic complexity with regard to the image patches in the vision transformer, in the vanilla vision transformer. So over here in this graphic, you can basically see the comparison, right? So there are 3 stages. In the vanilla vid, it always stays the same. So it's always the 16 by 16 patches. And then it's a global attention window, basically. And in Swin, you have hierarchical sizes of the patches. So first you start out by 4x4 pixel patches, and then you merge 2x2 to get these 8x8, and then you get 16x16, and you only compute the attention in these global windows. So basically these local windows. So these red windows are where the self-attention gets computed in, and that is more feasible actually, especially for bigger images. I mean, right here it's like 4x4. It's still okay for it, right? It's not that costly, but if you want to do some more fancy stuff, it might get more costly. So let's have a closer look at this Swin transformer. This is the architecture of the smallest version, basically. So it's the Swin T for tiny. And you can see we first have an image, height and width, and 3 channels, and then we do the patch partition. Here they say, okay, let's do it with 4x4 pixel patches. And then you get 48 dimensions because you have 4x4x3, 3 for the channels, right? So then you get a linear embedding that you put it through, and then the Swin transformer block. So there are basically 2 of them right here, right behind each other then. And then you get to the next stage where you first do a patch merging, which we saw before, right? Then you get bigger patches. And again, the Swin transformer block, and patch merging. So yeah, until the end really. So it's the architecture is not that complicated from this high-level view. You can have a bit of a closer look on the Swin transformer block in the next slide. No, first we look at the the different versions. So yeah, it's just really these 4 versions that were published in the first paper. It's Swin Tiny, Swin Small, Swin Big, and Swin Large. And here you see the number of amounts of the blocks really that are used, right? So you can see in Swin Tiny it's 2, 2, 6, 2. So it's always the number of transformer blocks that are chained together in each stage. And for the Swin Large, you have 2, 2, 18, 2. Well, for all of them, you have 2, 2, 18, 2. You just have a different dimension for the feature vector in the end. Okay, now we get to the encoder block. So on the left side, you see the Swin encoder block. On the right side, you see the vanilla vid encoder block. And actually for Swin, it's 2 blocks following each other, because that's that's the graphic that was in the paper, and I didn't want to create a new one. So you can see it's really similar, right? So first there's some norm, layer norm, then you do the attention. That's what's here. Here's a window, multi-head self-attention, that was useful, and then you've got a residual connection that is connected from the start to the middle, another residual connection from the middle to the end, and a layer norm and a multi-layer perceptron. Yes, so basically the encoder block is, you could say it's the same, just that the attention is computed differently. And yeah, I'll go on the next slide. Now we look at the patch merging in a bit more detail. I'm sometimes surprised about my next slide as well, so I'm maybe sometimes like, oh yeah, that's this one. So let's assume we have an image of Super Mario, of course. and the image has the size 32 times 32 pixels, right? So in the first layer, we get, or in first stage, we divide it in 4 by 4 pixels per patch. Let's assume that is true here. It's not completely aligned, but let's just imagine there are 4 pixels here and 4 pixels there. So the per patch, that would be 16 pixels. And for the whole image, that would be 64 patches. All right. Second stage, patch merging of 2 by 2 gives us 8 by 8 pixels per patch. And in total, it would be 16 patches with 64 pixels in each thing. And we just go on, right? So next one would be 16 by 16 pixels per patch, and it would be 4 patches. And yeah, in this example, we end with like one patch for the 32 by 32 pixels. So that's pretty easy, right? I mean, it's just merging pixels together in the stages. But now let's look at the window attention, actually, because that's what really is the more interesting part in this paper, is the whole window attention thing and how that can help us in getting more efficient, and also gives us the ability to look at finer structures. So as I said, we only calculate the self-attentions in local windows, and it's important that those are non-overlapping. So it's not like a sliding window. A sliding window usually is something like when you do convolution in CNN, right? So you slide the window some pixels further, and often they are overlapping. I mean, you can design them in a way that they are not overlapping, but yeah, often sliding windows are overlapping, and here we say, okay, we just have these non-overlapping fixed size windows, and this fixed size is also important to make it really feasible for the computation. So yeah, because with the fixed size, it has this linear complexity with regard to the patch number. And let's again look at an example. So let's say our fixed size, they always call it M in the paper, is 4. That means we have 4 times 4 patches per window. Okay, so it's 4 times 4 patches. And remember, each patch in here right now is 4 times 4 as well. So basically, the length of it is 16 pixels, right? So basically, it's 16 by 16 pixel window, but in patches it's 4 by 4. And each of these patches is then put through this linear embedding, so you get a linear representation of each patch and can then compute self-attention inside this local window. And that's what you do for the rest of the image as well, right? So in the end, you get 4 of those windows. They all have the same size because they have the fixed size, right? So you always really use the same size. And then you compute the attention. Now, one thing they noticed is that, okay, now that we have all this attention computed, we have one problem, and that is we don't have relations between the windows actually. So for example, like how is this patch here related to this patch here? Might be important in some ways, right? Because they are computed individually, we can't tell from here. So they say, okay, we do a shifted window. So what's a shifted window? They just move one of these windows by half the size, right? So it would be by 2 patches basically in X and Y. Now the example is here. So now you get this shifted windows. They are all shifted around. And what can we see now? Okay, before we had 4 self-attention windows. Let's count them now. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's way more than before, right? So suddenly we have 9 attention windows. So the naive approach would be to, we just pad them around here, and then we mask them, and then yeah, we get our attention. But then, wait, we have to compute self-attention 9 times now before we had to only compute it 4 times. So I mean, one of the main goals really of the paper is to be more feasible in computational resources than other transformers, especially than VIT. And because of that, they say like, no, we don't want to compute self-attention 9 times. So they do a little trick, which is called the cyclic shift. And the cyclic shift is basically just shifting parts of the image around, right? So we're shifting some windows, so for example, pixels. So we say, okay, we want to take 1, 2, 3, 4, and 7, these areas, and we shift them around in a way that we can compute it more feasible. And what becomes of it? So there's again this mask basically, right, that we had before. Then they shift it, and yeah, that's how it looks then, right? So we have 1 here, 2, 3, 4, 7. So what does that give us? Why do they do it? I mean, there is still, in a way, 9, yeah, 9 partitions, right? But now you can see there's this, yeah, the structure again that we saw before, where you have these 4 big windows actually. And what they do then is they compute self-attention in those 4 windows, and they mask out these areas. So they basically, through a smart masking algorithm that I won't explain in detail because yeah, there's one of those details that would probably take too long. It's really interesting. You can check it out yourself, this whole masking. But yeah, the explanation would take a bit of time. And yeah, it's through that actually they are more feasible. Yeah, because I mean they could also do the padding, and yeah, with the padding and the masking they could do it here, right? But then, or they could just say like, oh yeah, we just put some something here in between, and again we have four big windows, but then in each window you would have to mask 4 patches actually, right? So when you put like a cross in the middle here, you can imagine that there are 4 patches in each area, and then you have to do more masking than in this case. So in this case, the masking is, let me count, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? When you do it like this naive approach, it would be 4 times 4 would be 16. So yeah, so we have now 9 masks against 16 masks. To imagine it better, I put Mario in again, and yeah, you can see the Mario pixels were shifted around to here. Yeah, and it's actually quite interesting. I thought like, oh, how did they implement this? It must have been really crazy something. It's actually one function called in PyTorch. There's a method called roll, and when this roll method does exactly this, it rolls the pixels the way you want them. Yeah, so it's not that difficult to implement. Yeah, and this is how they actually showed in the paper. and when I looked at it in the paper, I was like, what are they doing? So that's why I prepared this little more detailed explanation for you with numbers and everything. Yeah, the window partition, the cyclic shift, as I showed you, put it here, and they used mask, multi-head self-attention, and then they do a reverse cyclic shift, which I didn't show, but yeah, they just reverse everything and put it back to where it was before. Okay, let's go on. Oh yeah, this one. This is one of the slides that I prepared last minute. It's just about the relative positional embedding. Because when you know transformers, you know there is this positional embedding that is used to take into account the position actually of the tokens or of the image patches, right? That you have. And yeah, they also use a relative positional embedding like the vanilla VIT does, with a change that they actually have a smaller bias matrix than VIT. So imagine in the vanilla VIT, you have like, yeah, a big number of tokens. So these positioner embeddings also have to cover a wider range, right? Because yeah, the token lengths or the number of tokens in one direction can be like 100 maybe, and then you have to cover these 100 positions. In the local windows, you don't have that problem unless you use a really big size of the local windows, because in local windows, the distances are way smaller, right? Even if you have a window size of 16, that is already a big window actually, 16 patches. So the range only is 16 and not 100. So that's why it's easier here to compute the positional embeddings than for the vanilla bit, for example. Yes. Oh, okay. That was an old animation. Okay, that's it. But then there was basically a level up. Swin version 2, which was released some months after the initial Swin paper. It didn't change the core functionality of Swin, so the shifting windows and everything still stays the same, but there were some improvements. You can see them here, and so on the left side there's a Swin version 1, and on the right side there's Swin version 2, and everything that's red is new. So, for example, really easy thing to see is that they moved the layer norm to not be before the attention, but after the attention, post attention, I think they call it then, right? So here the layer norm is after the attention, not before and after the MLP, and not before it anymore. Yeah, instead of the usual dot product for the self-attention computation between the query and key vectors, they now use a cosine computation, right? With a gamma hyperparameter there. And they also changed their positional bias thing. So yeah, from this standard relative positional bias, they did it a bit more sophisticated. We will look into it a bit now, but I have to say, this whole Swin version 2 thing, I have not looked at it in complete detail. So I'm not an expert on all these things they use here. If you have questions about it, of course we can talk about it, but I might not be able to answer them completely. But let's look at them. So what was the problem they were trying to tackle really with this layer norm moving here, right? Oh, they said, okay, in our experiments we saw that especially when we have bigger images, the activation values in deeper layers get really, really big. So they had a look like, what can we do about it? How can we lower these activation values? Because high activation values are just not good for training. They make it harder to train the models, right? Big activation values are not good. We want to keep the activation values rather small to have a easier training. So they came up with moving the layer norm, because they said, one reason why those values grow might be the residual connection. Because before we had this connection, let's look at it again. We had this connection, especially this one from the middle here, right, after the attention, right, to the end. So without this layer norm in between. And this, and also same for MLP, basically, because you feed it, and then you've got this residual connection from the MLP output. And so these output values were not normed. And then they had the idea, okay, we moved the layer norm and maybe that helps. And turned out it helps. So that worked. I will show you some graph on that here. Right, so we have comparison of this. So when it says as post, that means it's post attention. The layer norm is post attention, and pre is the layer norm pre attention. And you can see that all these triangular things are way under the circular ones, right? So the circular are the old versions, the triangular things are the new versions. And here you see the magnitude of the feature variance. And higher is worse. So this, for this big model, the huge model, actually it was really bad before they moved the layer norm, but after they moved the layer norm, it was actually really good. It kept really low. So that is an interesting trick that is quite easy to implement and helps. But they did a second one, and this is this cosine attention, cosine attention, of course. So they, yeah, instead of the dot product, as I said, for the self attention, they use this cosine computation with this gamma as a hyperparameter that you can set. And that is usually, I think they say around 0.01 or something. And this also helps in just keeping those values low. And yeah, that's one of the things I can't tell you much about in detail. It might be interesting to investigate why exactly that is. And yeah, feel free to have a look at it in more detail. And the next problem was the pre-train on small, they wanted to pre-train on small images and then fine-tune with a higher scale, right? So, I mean, it's again about this feasibility and the ease of training, because when you use smaller windows for training or for big pre-training, right, where you need the most load of images, it would be quite handy to be able to train on small images and then just do a fine-tuning with a smaller set of high resolution images, right? And they said, yeah, that is possible with Swin already, but then they see that the quality decreases. The bigger the images in the end you use for fine-tuning, the bigger the decrease of accuracy is, basically, especially in image classification. They showed that. So the solution is something with a really long name, log space continuous relative position bias. That is what? Right? What? So let's just look at it. And yeah, so they use a meta network actually instead of just this matrix thing. A meta network is a two-layer MLP that generates these positional biases for arbitrary relative coordinates. How that works? Good question. They don't go into detail on that really. Yeah, it's probably something you can discover when you train it yourself, or when you look at the whole implementation, or when you even implement it yourself. It's also an interesting thing to investigate. And they also say that they don't just use the linear scale of the coordinates, so not like 1, 2, 3, 4, 5, but they use the log space. Because in log space, actually, again, saves a bit of computational power, because the differences in the end are not as big in total values, right? Because when you just count in integers, it's way bigger than when you're in log space. So I hope you can imagine that. Anyway, I didn't have much time to think about this before the presentation, but there is this nice visualizations in the paper about just this. So here we have basically a window, a local window of size 8 by 8, right? So we have a 8 by 8 window, and then we have the version 1 positional embeddings, then these continuous positional biases from the version 2, but in the linear space and then in the log space. And yeah, we can see that from the version 1, that stuff is a bit diffusing and just not as on point really as those new approaches they came up with, right? And when it's on higher resolutions, it even looks nicer. I believe those can be some really trippy images when you animate them. But yeah, it shows that just these continuous positional biases work way better and way more on point than those relative positional embeddings they used before. And that also shows in the experiments. Do I have something about it? Maybe yes, maybe no. Okay, now let's first look at this, because there are other optimizations that I won't go into detail right now. So they use self-supervised pre-training for their biggest models. Yeah, actually, the Swin version 2, they have one version that is they call it Giant, and that was actually the biggest vision transformer at this date. When they released it, it was 3 billion parameters, and that's where they use the self-supervised pre-training mostly. And then there is some more names. It's just for you to check out if you want to go into more detail on this. It's serial redundancy optimizer, activation checkpointing, and sequential self-attention computation. So those are like yeah, minor things they use that help them improve their performance even more. And yeah, so here's a little bit like how they performed on the ImageNet 1K classification. And you can see the Swin version 1 up here in the big and large models, and the Swin version 2, big, large, and the giant one. Here you see 3 billion parameters, right? And in between something like the width G and some others. And yeah, we can note that this giant model is the best, actually, also better than the width giant one, with 84% top one accuracy here on the ImageNet yeah, 1K V2 dataset. And we can also see that the pre-trained time, right, is, for example, for most Swin models, way lower than for the WIT one. So that is in, here they say TPU V3 core days, right? That's the measurement, TPU V3 core days. So yeah, I mean, that's one of the main criticisms for the WIT paper, is that they just use this amount of yeah, core days that no one can afford except for people working at Google, because 30,000 TPU V3 core days is just very expensive. So it's better to have about 30 or 20 TPU V3 core days, and you get quite a good accuracy with that already. And also, of course, yeah, the parameters is yeah, a better range than this giant model, for example. But they not only did classification with Swin, because that's a nice thing about it, they can also do segmentation, for example. Here's a segmentation benchmark, the ADE 20K. Well, they also show that at the point when they published it, they were the best ones with their giant model. And yeah, also for object detection, actually, which is here. Yeah. Well, in the end, they show that their giant model just beats everything. But then again, it's a giant model, and yeah, it is quite big and can do a lot of stuff very well. Okay. In the end, congratulations, you made it to the end. I do have some code prepared, actually. Let me just quickly open it, because the Swin Transformer is available in the Hugging Face Transformers library, of course. And it is the version 2 implementation. So when you want to have a look at some details, like how are they implemented in this or that way, you can just look into the Hugging Face code. There you will see most of it and can navigate through it and see how that is implemented. And yeah, I did a little notebook here, and just basically one is just the example for the classification, the Swin image classification. That is, you can also find it. Oh, oh yeah, I shared the wrong one. Wait, can I change that? Okay, I quickly stop sharing, then share again. Wait a second. Yes, now? Okay, great. Yeah, so it's Visual Studio Code, right? So yeah, the first thing really is just the example you also find in the docs, really. So you can just load some data set, for example, this cat image. Oh, let's just basically run it, right? Import transformers, torch, dataset, blah, blah, blah. Load a dataset, get an image. This one of the cats, for example. I think Niels uses it quite often, right? And then you can get the feature extractor, so the auto feature extractor actually. So you just pass in a model name, and here you have this model from the Hugging Face Hub from Microsoft. So it's a Swin Tiny with a patch size of 4 and a window size of 7 on a pre-trained on an image size of 224 images. That's how they label, or that's how you can read those model names. And then you can just import it from pre-trained this Swin for image classification model, for example. The feature extractor is actually the same that is used for the vanilla vision transformer. So it just reuses the one. So we loaded it. Then we have our inputs. Okay, feature extractor, put the image in there, return tensors, PyTorch. Then do the model, get the logits from it. And then you can get the predicted label, right? It says tabby cat. I think it's about right. I'm not completely familiar with cat races, but I think it's not completely off. Yeah. I did a little example by myself then, because I wanted to see, okay, does it work with other data as well? And I had a look, okay, what pre-trained models are there? And I found one that was pre-trained on the Eurosat data, so satellite data actually. So let's load the data set. It's also uploaded by Niels here. Then we just get some random sample this time. This one here. And the class label, which is pasture, apparently. And now we're just doing the same as before, right? So this time the model is not from Microsoft, but some user called Gmol. And here the Swin Tiny patch for Windows 7 224 fine-tuned Eurosat. Basically the same as before, but with Eurosat, right? So let's load it from the hub. And then you can again do inference and we get its pasture. Yeah. So it worked out quite fine. That is really simple to use, really. If you want to use it it for classification, it is extremely simple. For segmentation, I tried to get it to work. But actually, I think you have to use a framework for segmentation. So basically, the Swin here is only the backbone, right? You won't get the whole pixel maps just from the model, but you have to get some framework like mask, RCNN or something, and plug the Swin into it as a backbone, and then you can get the segmentation as well. And I'm still working on a fine-tune example. I will share it in the Discord actually when I'm done with the Swin fine-tuning example in Hugging Face space. So that's still under construction. But now I'm really at the end with my examples and everything. And I think it's question time. If you have questions, feel free to ask them now. Yes, it's still running. So I got it. I hope it all worked and the sound is on it and everything, but I think it should be fine. Okay, great. Yeah, as I said, I had a lot of fun doing the presentation. I laughed a lot and yeah. Sure. Swin. Okay, wait. I think you have to stop. Good question. I haven't thought about it. I am just looking for the Swin paper. Wait a second. If anyone else has ideas, of course, feel free. I'm just getting the paper and then I share it. Yeah. Ah, okay. Wait a second. This one? No. Here? Okay, so are there more? I don't know. So basically, what is this Swin doing? Is it, can you quickly explain it? Okay. And that is somehow not working as well as with ResNet or anything. Yeah, no, no, it's totally fine. Just have to think about it because, yeah. Hmm. So you think it doesn't just, well, it doesn't cover the overall, you say global coherence as well as a convolutional network like ResNet. You see. Which ones? These ones. On the very left? Oh, yeah, well. That's true. Yeah. Yeah, interesting. I would definitely look at that because I haven't looked at this dice when I didn't even know it existed really. So yeah, I think this whole Windows thing. I mean, it's mainly because it's similar to existing convolutional networks, right? The whole architecture, and I think that's why I guess most people are able to deal with it easier or plug it into to other existing frameworks and everything. So that's these windows are just, yeah, I don't know, similar to what convolutional networks do, right? And yeah, long range transformers. Uh, well, I mean they're more of a transformer kind, right? Yeah, yeah. I mean it's quite interesting to see all kinds of approaches, really, right? In the papers, it feels like there are so many papers and so many things they're trying out. And you always wonder, okay, why are they doing this? And we already have that one, and it works well. But then other people want to try other things, and there's so many papers um, also that build up on the Swin transformer, right? And that somehow change it. And I also saw the one about neighborhood attention transformer, which has a total different take on it again. And yeah, so. Uh, it's really why does any network exist, right? Because people want to publish papers and want to show off. Okay, any more questions? If not, feel free to hang around in the Discord, I guess. I think that's Merv's part actually, to say we are still in the Discord channel. I actually have to catch a train, but I'll be on my phone in the Discord channel. So yeah, feel free to ask. If you didn't want to ask in the big round, you can also message me. I plan on creating a Notion notebook actually, where we finally can collect our computer vision study group resources so that you can look it up as well. Yeah, when I have created that one, I will also share it here in the Discord. And then you can look at this awesome presentation again. But you should look at it in animated way actually. when you look at it in a non-animated way, it looks horrible because there are so many layers overlapping. So yeah, only animated. Well, thank you for attending, and yeah, have a good day.